Okay, welcome everyone to our webinar at IPMS with the topic two-photon polymerization, 3D printing for high-resolution rapid microfabrication. My name is Thomas Stoppe. I'm working at Cognitive Sensors at Fraunhofer IPMS. Today, Tim Schulze will present our slides, which we prepared. Tim Schulze itself, he graduated as a master's in physics at the Humboldt University in Berlin in 2018. Afterwards, he started his dissertation with the title MEMS-based components for modulation of terahertz radiation in hollow waveguides at Fraunhofer IPMS and at the BTU Cottbus. And he just finished his work also using two-photon lithography, which is why he will now present the topics we are working on with this technology. Questions can be asked during this meeting in the questions box, and we will answer them after the presentation. And I wish you much pleasure with the presentation, and I hand over to you, Tim.
Thank you, Thomas, and thanks for the audience for joining in. So like Thomas said, I want to tell something about two-photon polymerization lithography, the things we have been doing, and also a general background concerning this technology, and also what we are planning to do in the future. So let's start with the basics of two-photon lithography. So basically, we start out with a substrate that hangs upside down, and on the bottom of the substrate there's a negative photoresist, and this negative photoresist polymerizes when UV radiation illuminates this. And we, in this case, use a laser, infrared pulsed laser that beams its light into the photoresist. And well, like I said, we need UV radiation for the polymerization. But in the center of this beam, in the focus, the intensity is so high that it can actually happen that two photons are absorbed at the same time. And the energy of two photons absorbed at the same time is equivalent to the absorption of one UV photon. That's why the resist polymerizes, but only within the small volume in the focus. This focus is also known as the voxel. And so the beam is scanned through the substrate and thereby creating different structures. And yeah, we can build a lot of interesting things. And once we're done with our desired structure, for instance, this pyramid here, we could just remove the objective, and there's still some resist left. And with a bunch of chemicals and solvents, we're able to get rid of the remaining resist, and then we are left alone with the substrate and the desired object we have been printed. So let's zoom in at the focus here, the voxel, so the volume where the polymerization happens. This volume, it's not really a ball shaped, a circular shaped. It's more like an ellipsoid, and the shape is indicated here. So it has a smaller lateral width and a longer width along the axis, and it's sort of look like a grain of rice. And this really needs to be considered when printing our structures. For instance, this one time I tried to print a horizontal gaps over each other. So maybe you can look in the camera now. I'm showing something with my hands, and due to the shape of this voxel, I wasn't able to really print the structure. But the solution was I just tilt our structure by 90 degrees, and then I was very able to print the desired shape. And one more thing, the process for the polymerization here is based on two-photon absorption. And two-photon absorption is a nonlinear optical process that is relative to the intensity squared. And for this reason, the resolution of this process is way higher than, for instance, for normal UV irradiance with a UV laser that is, for instance, used with stereolithography. And the system we are using at our institutes was fabricated by this company Nanoscribe, and the system is called Photonic Professional. And just I want to go over the specifics real quick so you have a rough idea of the capability. So like I said, it radiates the negative resist with infrared radiation, and we got a maximum whiting field of approximately 100 by 100 millimeters, so 10 by 10 centimeters. So we're actually able to build really, really wide structures in the domain of even centimeters, although the height is limited, in this case by approximately 8 millimeters. In our institutes, we have 3 different objectives we are using for our components, and depending on the size, you could either use an object with a really, really high numeric aperture and a really small voxel, or a big voxel in case of the tenfold magnification objective. And it's really a trade-off when you want to print. It's a trade-off between printing time and structural resolution, and then you decide for which objective you go. And what I indicated here is the aspect ratio. For instance, the voxel for the tenfold objective, it has a lateral width of approximately 1.5 micrometers, but the aspect ratio is 10. So it's 1.2 millimeters wide and approximately 12 micrometer long. So in case you want to print something with a really, really high resolution, you should really consider the orientation of the printed object. Here, and on the other hand, we tried to develop the whole process chain from the fabrication, from the design, the fabrication, the characterization institute. So we have different opportunities to characterize printed components, like with raster electron microscope, digital holography microscope, infrared microscopy, or just ordinary optical microscope, digital microscope. And we recently just got a new laser scanning microscope, and it's really exciting, especially in the last case, because we now have the capability to measure just random objects like chips or anything else with a laser scanning microscope, get CAD data from it, and then we can use this CAD data again to print the component, like to make a copy of it. And also we have quite excessively used sputtering for our objects. So in case there are interesting questions concerning the metallization of such structures, I'm happy to answer them. And also O2 plasma activation, selenization, and part removal. So there's been quite a few things we have been done and we can achieve in our lab. So let's give you some examples of what we have been doing. So the idea with the following slides is give you an idea of the scale we can print structures. So here you see the scale from several hundred nanometers up to centimeters. And if we start with the really, really small things, we can see here test structures where was just a test. Here was a single voxel line in the middle of those triangles, and was just to find out how the printed line behaves in different distances compared to the substrate. Yeah, because sometimes we had issues when printing really special structures that the intensity was too high on top of the substrate, and then bubbles appear, and with this parameter sweeps we find the proper printing parameters. And this was just a test structure we've been done. It is those prominent wood piles, so just single lines printed in this wood pile configuration, and you can see here that we were able to reach a width of approximately 100 nanometers. So let's scale up the size of it. Another thing we are very happy to have achieved is printing on actual chips. So usually when you have your system, you have special substrates to print on, and it was quite hard work to finally be able to print on chips. And this has been done by one of my colleagues, Severin Schweiger, he printed on so-called CMOS, capacitive micro-machined ultrasonic transducers, or basically just chips that can emit ultrasonic sound and also detect ultrasonic noise. And in order to do impedance matching with the chip and the surrounding to increase the power transmittance, a so-called impedance matching structure was printed on that. And so it's just a block with some holes in it. And yeah, we were very happy that we could finally achieve such things. Next step, one size bigger. Here is just a little test of the so-called C60 molecule, or also called the buckyball. And also we use this, colleagues of mine use this for acoustic metagratings. So the idea was to use the metagratings to shape the wavefront coming from ultrasonic transducers. And this has also been published, and according to my colleagues, they were quite satisfied with the results of this. And here in a higher scale, you can also see this metagrating that has been designed. So yeah, this was just put in front of one of our ultrasonic transducers, and by this we were able to shape the wavefront of our substrate. And another thing I want to point out is this image here. So this is again a parameter sweep about over different printing parameters, different printing laser intensities, and also scanning speeds. So whenever we build something, a laser scans through the structure to polymerize certain areas, and this scanning speed can also be addressed for parameter tuning. And here we are currently trying to establish a non-destructive testing process of our structures. The idea is to use, so let me start differently. We are able to change the E modulus, so the elasticity of our printed structures by addressing different printing parameters. For instance, if we use low laser intensities, we're able to print structure that a little bit softer, have a low Young modulus, or if we increase the laser power, then the structures are a little bit more stiffer. And with Raman spectroscopy, we were able to measure this stiffness. And yeah, like I said, we are currently trying to establish a process to determine the elasticity of our objects without even touching them. And a next step up, this is also a project we have been done. This is nano imprinting lithography, and the idea is of those little spikes is to use them as some sort of a printing substrate, and to push them into the coating or the resist coating of a specific wafer, and to imprint those structures into the resist. And once you do an etching process on those chips later on, we are able to transmit those structures into the chip. And this is also successfully done. And last but not least, just some small demonstrator to show how big we've been able to print. For instance, you may know that at Fraunhofer IPMS, ISS, we have a location in Cottbus, and this is a library of the Cottbus University, and we've been able to print this little library. So usually this library is approximately 33 meters in height, and here it's approximately 5 millimeter in height. And it's just a lot of things we've been printing. For instance, this is just a holder for the acoustic metagrading we've been using. And it happened a lot of times that we needed specific components for various objects. Like here, it's a small cap for vacuum volume. And we couldn't find anything on the market, so yeah, we just printed this cap and had some excesses for the tubes to put on, and it's really a universal tool. We are very happy about that we bought this system. And on the other hand, it's also important to really get some experience with all the issues this system could have. Something you need to consider when printing structures. For instance, if you have very long, very large structures and long printing times, it can happen that various things can happen. For instance, usually the objective is always inside of the resist, but sometimes if the structure gets too big or too large, it can sometimes happen that the objective loses touch to the resist, and then it's not printing in, it's not illuminating light in the resist anymore, but in free space. And such things need to be considered when printing, and just need some experience. And also the summers were really hot in Germany and in the lab. If it's not able to control the temperature, this could also lead to some little deformations in very, very tiny structures. And this could also lead to results they are not happy about. So this really needs to be considered when printing your structures. And on the other hand, if the structures are really tall, it can also happen that during the washing of the resist, when you're done with your component and you want to get rid of the resist, that structures get deformed by surface tension of the solvents. And for that reason, we figured out that critical point drying is quite helpful. And also in this case, structure can a little bit temperature resist sensitive, and it's a lot of try and error. And in case you have ideas for printing something, I guess we can figure something out to address those issues. And in the meantime, also reflectance can be an issue when the structure is really close to the substrate, and transmission can be an issue if the laser intensity, for instance, is too high with certain substrate. It can heat up and can form bubbles and stuff like this. So at first you usually do some for specific specific structures, we need to do some parameter testing to figure it out. And also the removal of parts can be quite complicated. With large structures, usually no problem. Even me, I picked up little structures with a tweezer very easily, but small structures can also be quite challenging. And usually if you have high aspect ratio structures, for instance, little holes in your structures, it could also sometimes be possible that you are not really able to wash a resist out of this. And yeah, just a lot of trying and gaining experience with that is necessary to be very flexible in your in the things you are doing. And last but not least, I want to give you an example of the things I personally have been doing a lot with the printing system, and where I was super glad to have such technology on my hand. So I've been working with hollow rectangular waveguides for terahertz radiation, and those waveguides are indicated here. So it's just a tube with a rectangular profile, metallic sidewalls, and a terahertz radiation can propagate through it. In this case, for instance, it's at 600 gigahertz. And the issue with those waveguides is that they have a specific cutoff frequency. So waves are only able to propagate within this tube if the propagating frequency is higher than the cutoff frequency. And for instance, for a waveguide with this dimension, the cutoff frequency is only depicted by the width of the waveguide, and this is approximately 400 gigahertz. And now the idea was we want to develop a terahertz switch. So just bending beams close to waveguide And actually, I forgot one thing. We actually had this idea of developing this in silicon as a real silicon chip, but it was very exciting to also try this with a printed object, because the resolution we are able to obtain when printing structures in a silicon chip, they approximate in the same order of magnitude size-wise with the resolution of this printer. And that's why we did a rapid prototyping approach to print this switching capability inside a printed component. So basically the idea is to have a waveguide there where the bending beams close it, and this decreases the width of the waveguide. This increases the cutoff frequency, and eventually this cutoff frequency is higher than at 600 gigahertz, and then the signal is attenuated. And the first time I did this with static structures, so not real bending capability, but I did a parameter sweep over different components. For instance, here you see the CAD depiction of my waveguide with sort of bending beam inside with zero deflection. And then I did a parameter sweep over different other components where the deflection is a little bit higher. For instance, here it's a 120 micrometers. And here I think it's a little bit better to see. So here zero deflection, and here bending beams with a 120 micrometer deflection. Finally, we got our printed object. We metallized it with gold. Gold is really great for metallization of such substrates for sputter coating. And in the end, I put this in a metal holder. And of course, I showed you the waveguide. It's a tube that is enclosed by metallic sidewalls in all directions, in all four directions. And on top of my printed component, I put another metallic block. And then in the end, it's looked like this in my design. And for the terahertz characterization, we used a really broadband terahertz source indicated here at the position 1, and we just use mirrors to illuminate this broad terahertz spectrum into a waveguide at 4, and then just collect the same radiation again with mirrors till it gets into the terahertz detector. So this is how it looked like. Really simple setup that was able to characterize our different waveguides components. And here we can see how it's turned out. So what we see here is a terahertz spectrum, the initial spectrum that was illuminated by our source and detected by our system without a waveguide. So you see it starts with a few hundred gigahertz and goes on over 1.5 terahertz. And we don't see a cutoff frequency, nothing, just some small spikes, absorptions from the water in the atmosphere, but that's it. But once I put in my waveguide, we could actually see that there's a cutoff frequency that appears. So the spectrum I have been measuring is the blue line here. So this is really the stuff I have been measuring with my terahertz system. And the red one was the simulation of the transmittance of my waveguide. And we can see a very high degree of overlap between our simulation in an FEM simulation and our real printed and our result from our printed component. And so what did I do? I exchanged my printed component with another printed component with a different deflection. So here it's 20, it's 40, and so on till 120. And we see that the cutoff frequency moves on, and still high degree of overlap between our simulation, our measurement, and in the same time, the waveguide is usually only used within this frequency band from 0.5 terahertz to 0.75 terahertz. So when you have a signal within this band, you can also see that it gets attenuated by doing this switching process. And by this parameter sweep, I was able to give a proof of principle of my idea. Not even I was not even using silicon technology for this, so just the printed component here, and we were very happy about the results here. So a small giveaway, a summary of our ideas. So we were able to do all kinds of rapid prototyping with our printing system in the terahertz domain and in the RF domain, acoustics, electromagnetic, in the acoustic domain, but it's also possible to print electromagnetic meta surfaces or meta materials. It's also able to print optical microcomponents and also those masters for nano imprintement lithography. And I tried to show you that the capability ranges from a few hundred nanometer up to a few centimeters, and this with resolutions in the area of 1 micrometer. And in case you feel confident, if you feel like working with us together, so we have the whole processing chain from design, fabrication, and characterization. And with this, I'm really looking forward to get interesting questions from you. And thank you very much for listening.
Thank you very much, Tim, for this interesting presentation. I will look at the questions. I got one question so far. If any other questions occurred, please raise a digital hand or write them in the question section. Tim, first question. It's about upscaling. So how fast is the printing process, and can you think of so how big is the gap between industrial processing, so high throughput, and how fast can the process be in terms of wafer production, so printing meta surfaces on the wafer, for example?
So the way we used it was for now mainly for rapid prototyping. And for instance, for this structure here, you can see approximately the size, so almost approximately a millimeter diameter. And the printing here took approximately 4 to 5 hours. So currently we are not able to print on a whole wafer a lot of structures on a whole wafer, but it's not our goal. Our goal is to show that specific technologies are possible and to do this rapid protein characterization. But I think the company NanoGuide, they are constantly working on improving the system to increase the scanning speed, and I'm confident that in the near future they will find solutions to increase the printing speed of such systems. But for now, we unfortunately have to rely on rapid prototyping of small structures. But on the other hand, I mean, for some applications, it's not really necessary to print on a whole wafer. For instance, in this case, with this nano imprint lithography, we can use this master and several times to print those structures into the wafer. And I mean, for this, the processing speed is way higher. Yeah, so it really depends on the specific idea or on application concerning the speed.
So I mean, the kind of structures you can print, let's say at once, so not one after the other?
Yeah. So one spike is approximately 30 minutes. So this can be printed in no time, and then it can be used numerous times. Yeah. But
okay.
if you want to print such matching steps on a whole wafer, then this will take a lot of time, and there needs to be
some mask, or you transfer it to silicon.
There needs to be improvements done on the system, but I guess it's technology wise possible to parallelize the printing process here. But as far as I know, it hasn't been done yet.
So the way to go would be to transfer it to another technology, maybe using mask or something to get print on a whole wafer if it is too
then
difficile, for example.
This would be more straightforward, but in the meantime, the advantage of rapid prototyping in this case is that it's also way cheaper than developing masks and printing in silicon. So this was the whole idea, to get a really fast and cheap proof of principle for our scientific work.
Okay, thank you. I hope that answers the first question. Okay, the follow-up question from the same. Are there many materials to play with? So what is the material range? I think you showed some on the one slide, but yeah, can you something say about the material range?
So most of the resists that are commercially available from the company Nanoscribe are based on acrylic resists, negative resists, and they're also silicon-based resists who are way softer, and also positive resists are available, but they have only, especially those acrylic-based resists, have only small differences concerning their dielectric properties. But they're also, for instance, when we talk about optics, there are especially resists developed to print optics, like little lenses, for instance. Yeah.
Okay, thank you. Okay, next question. You raised your hand, Shay Yulsari. You want to talk? Otherwise, I read the question. Okay, I'll just read the question. Can you please tell what are the material properties, modulus, and strength you can print? Also, can you tell what is the typical surface finish you achieve? So material properties, and if you can say something about this and finish.
Let's start with the material properties. So my last slide in the back, I collected a few resists that are commercially available for printing here. So these are the names of the resists, and here you can see average Young's modulus for those structures. And the publication we have been doing about changing the Young's modulus by addressing the printing parameters, we've been able to tune the Young's modulus between 0.6 and 0.5 approximately, 0.6 and 1.5 GPa. Yeah, and so this is what we achieved there. And what was about the mechanic properties?
Yeah, this was about the properties, modulus, and strength, and the other question was about typical surface finish. So I think about roughness, for example.
Roughness, yeah.
So surface finish, how does it look like? Maybe in terms of roughness, for example.
So when printing very high resolution structures with the, for instance, with the 63-fold magnification objective, their surface roughnesses of only a few nanometers. But when I worked on my terahertz waveguides here, okay, maybe you see some scratches here. They are not from the printing process. This is because of me, because I handle them a little bit rough. But maybe you can also see that it's not perfectly smooth here. I mean, it's very smooth, but not perfectly. And when I applied gold on that, I was able to measure a surface roughness of about 0.4 micrometers. So there are different measurements for surface roughness. So I'm considering the RA value here. So the RA value here was 0.4 micrometers. And this is what we attained here. And maybe another thing I need to address here concerning the surface roughness. So I told you that the printing field can be as big as 10 times 10 centimeters. But this is only the way the stage can move. The objective that prints certain structures, the objective doesn't have an aperture of 10 times 10, so it doesn't have a glass window or aperture of 10 times 10 centimeters, so this is way smaller. And for that reason, we have to stitch our printing areas together. It can be seen here. So for instance, here see this little structure. This has been printed by the objective in a steady position. And once this structure has been printed, it needs to move on to the next area and print there. And then those structures are printed together. And those can also lead to specific surface roughnesses above several microns. Yeah, but in the end, it really depends on your application and what you need for what sort of roughness do you need. So it's really a tricky question that maybe if it's really interesting for you, we can talk about this afterwards.
Okay, good point. Okay, I hope the question is answered. Please specify the question or raise your hand if you have questions in more details. Okay, next question is, thank you for the interesting webinar. Are optical components printed with this method transparent in near infrared regions, so from about 800 nanometers to 1000 nanometers?
I must be honest, I don't know. So the lenses that are that can be printed, as far as I know, they are definitely for the visual area. For near infrared, I'm sorry, I really don't know. I need to check this. Maybe you can reach out to me and then I can answer this afterwards.
Okay, just reach out to us if you like.
We can print mirrors. That of course that's possible. We can print mirrors, metallize them, but transmittance in the infrared, I'm not sure if there are some specific absorptions. I need to check.
Okay, thank you. So next question is, do you have any experience in printing refractive and or reflective optical lenses? So it is in kind of this direction if you have experience in this field.
No, we don't have done this already, but we had this idea of printing diffractive gratings for spectrometers. So this can easily be done with this system, but refractive optics is diffractive optics are definitely possible with this system. Yeah, we just need a specific design. Maybe if we want to do this, maybe you can send us a design. We can print this in no time, and then we can do an evaluation, and then we could see how successful we are with this. I'm really confident that this works, but unfortunately, we don't have any experience with this yet.
Okay. Next question, do you have experience with printing micro-optical surfaces, for example, microlenses and or optical structures on top of an image sensor surface?
So there are publications that have done this, and it's definitely possible, but also we have not done this before, but feel free to contact us afterwards, and I'm happy to discuss this. But I'm very confident that this is possible, because we have also already achieved printing on CMUTs, those ultrasonic transducers. So very confident that this will work.
We will figure this out correctly. Okay, so last question. If you have any other questions, or hopefully I haven't overseen any question, feel free to raise your hand or type another question. So last question by now is, do you offer printing services for others, or do you just use it for your own research or collaborative research?
No, of course we we accept offers. If somebody wants to work with us and is interested in using our experience with that in our system, we would be happy to. If we reached out to us.
Okay, thank you. Okay, these are all questions I can see so far. So thank you very much again, Tim, and thank you for your attendance. You will receive the slides and the link to the recording, I think, by tomorrow. And yeah, as Tim mentioned, we are inviting you to a discussion about your questions or any other topic you're interested in. So just reach out to us via phone or email or any other type of communication device you can think of. Thank you very much for your interest and have a nice day. Bye-bye.
Thank you. Bye-bye.